Okay, good morning. So we are going to start, thankfully, all of the classes are in the same place. I made sure to end everybody after we talked about the 3-group examples. And so now we're going to move on to the 4-group examples. Okay, so I'm going to go back over to the simulation and we're going to go ahead and add 4 groups. Now, this one starts to look different because we're no longer dealing with a planar molecule. So we're now fully in 3 dimensions. And the angles are, don't try too hard to figure it out because you can't really, you're not dividing 360, by anything anymore because we're not talking about a flat surface. Okay. So the name that we give this when there's 4 groups, so this is whether they're bonds or whether they're lone pairs. When there's 4 groups surrounding the central atom, we call this tetrahedral. Okay, that's the electron geometry. The molecular geometry in this instance is also called tetrahedral because remember, any time that the electron pair group surrounding that central atom is a bond, that all of them are bonds, then the electron geometry and the molecular geometry names should match. Okay. Now, if we replace one of those groups with a lone pair, you can see that the name of the molecular geometry changes. So the electron geometry stays the same because you still have 4 groups, but the molecular geometry changes name because we're now looking at kind of the outline of these 3 groups that are extending from the central atom because we just want to kind of trace the outline of the atoms. Now, just to be really clear, this is still stemming from the tetrahedral geometry, electron pair geometry. And so this set of 3 atoms surrounding that central atom is not the same as if there were 3 atoms and no lone pair. Okay, so we'll do an example of that on the notes in just a second to show you the difference between something like BH3 versus NH3. They all have 3, or those two have 3 hydrogens, but the NH3 is going to have a lone pair, and so that's going to change its geometry. Okay, the last one here that we need to consider that has 4 groups is with 2 lone pairs. Okay, so this one's interesting because the electron geometry still takes on that tetrahedral shape. So if you picture all 4 of those groups, it still looks tetrahedral. You can kind of rotate it like this so that it looks more like the other one did. But now when we just look at the outline of the atoms, this is kind of looks very similar to the bent version that we called it before when we had 3 groups and 1 lone pair. The difference is the angle here. Okay, so we didn't do the angles earlier. Let me go back to 4 bonds. Okay, so when we have 4 groups surrounding the central atom, the angles between the bonds are 109.5 degrees. And that would be the predicted angle anytime we have 4 bonds. So with a lone pair and 3 bonds, or with 2 lone pairs and 2 bonds. Okay, predicted that it's going to be 109.5. Remember, though, every time we add a lone pair, the real bond angle decreases slightly. All right, so we will look at a couple of those examples in just a second. Okay, so here are our actual examples that we're going to consider. We're going to look at CH4. Give us a little bit more room here. Okay, we're going to look at CH4, NH3, and H2O. Now, if you want to go ahead for Lewis structure practice and go ahead and pause and draw the Lewis structures, that is a great idea. This is what you should get, though, for each of the Lewis structures. Okay, so every single one of these has 4 groups. Let me make that a little bit bigger. Okay, 1, 2, 3, 4. all of those are bonds. On the NH3, one of them is a lone pair, 1, 2, 3, 4. And on the water, two of them are lone pairs, 1, 2, 3, 4. Okay, so for every single one of these, electron pair geometry, I think the simulation just calls it electron geometry. Let me move this to the side a little bit so we can add these labels. Okay. So for every single one of these, the electron pair geometry is tetrahedral. And the predicted bond angles, let's see, just move that up a smidge too. So predicted angles for each of these is defined by the number of those groups. So it's 109.5. Okay. So looking really quickly at the real models, we go down here to the bottom and click on real instead of just model. Let's start with CH4 and let's turn on all of these to show us the answers for all of these. So the molecular geometry is also called tetrahedral since all of those are bonds, and the angle, the actual angle, is 109.5. Okay, this is what we would expect. So molecular geometry is also called tetrahedral, and the real angles are also 109.5 here. Okay, NH3, one lone pair. The geometry, the molecular geometry is called trigonal pyramidal, and the angle has decreased slightly. It's down to 107, 108, down from 105, 109.5. Okay, so you don't have to know the exact amount. I'm just going to put less than 109.5. And the name of the molecular geometry is trigonal pyramidal. Okay, last one, water. Still four groups, still an electron geometry of tetrahedral, but now the molecular geometry is called bent. This is different than the bent that we saw earlier with three groups. Okay, I'm going to write it down and then we'll talk about that. The actual angle is even more less than 109.5. So to indicate that, I'm just going to put 2 less than signs. All right. Recognize that the SO2 up here, this was called bent as well, but it's bent with 120 degree angles. And this one, or slightly less than 120. And this one is bent with less than 109.5 angle. Okay, because it stems from, the water stems from 4 groups, not 3. So they give them the same name. They're not, they have the same general shape, but water has a little bit smaller of an angle. Okay, all right. I realize it's starting to feel complicated to keep all of these together. So here is the, it's a cropped version of table 11.1 that just covers these first set of groups. So 2 electron groups, 3 electron groups, and 4 electron groups. And then it breaks them down by how many of those are bonding versus how many are lone pairs. So this is the number of the groups that are bonds. This is the number of groups that are lone pairs. So it really is just summarizing. In fact, it was the exact same examples. I guess I'm not that surprised, but we did do a different one than CO2 up here. Or maybe we did both that and something else. Anyway, it gives you the breakdown. If all of them are bonds, the names should match between the electron geometry and the molecular geometry, right? It's only when we start to add lone pairs that gets different, the name of the molecular geometry versus the electron pair geometry. Okay, so good summary there. So we're going to do a couple practice ones, and then we're going to finish off with 5 and 6 groups. So if you go look, I'm sure I have this later on, actually. Let me see. Oh, that's a lot of practice. Oh, we don't even do 5 and 6 groups till later. Is that right? Let me see. Well, where did they go? That's definitely for Friday's class. Oh, okay. I think I have the 5 and 6 groups embedded in the examples here. So we're going to have to, yeah, I'm going to have to pull up the rest of this table from the textbook. I should have put it in the notes, but I'll go ahead and pull it up from the textbook and we'll talk through those ones as well. Okay, so let's do these few examples first. So go ahead, what I would do, go ahead and pause, do the Lewis structure for CH2, go ahead and try to assign electron geometry, molecular geometry, and determine the bond angles. And I want you to try to build it in the simulation and visualize what it looks like in 3 dimensions. Don't leave these blank until later. You guys are totally ready to do this. Okay? All right, so go ahead and pause the video now. I'm going to finish it off. Obviously, when you unpause, you'll see me working through the example. So if you're struggling, you can just sit there and watch me work through it. But it's always better for you to try to practice it on your own first. Okay? All right, so 3 groups surrounding that carbon. So the electron geometry is called trigonal planar. The molecular geometry, because they're all bonds, is also called trigonal planar. And the bond angles should be 120 degrees. Now, I'll show you what I mean by build this in the simulation. I'm probably not going to do this every single time. But like we said that there was a single bond and or 2 single bonds rather, and a double bond. So this is what the purple one would be, the carbon, the double bonded one would be the oxygen, and then the single bonded ones would be the hydrogen, okay? So when you say trigonal planar, I want you to be visualizing this. This is why we're using the model, because I don't want you to just regurgitate the name to me. You know, if it's 4 groups, I don't want you to just say, oh, of course it's tetrahedral. I want you to actually know what a tetrahedral geometry looks like. Because when we start talking about polar molecules on Friday, that's going to become really important. All right, CO2, we did this one already. We'll go through this kind of fast. Again, good practice for you to go ahead and pause. Okay, there's that one. CCl4. A lot of these we already did already, or at least very similar versions. You should be hearing this after you already worked this example by yourself. Because although we may have done it already together, it's very useful for you to pause and do it. That's the difference between these recorded lectures and in class. In class, I sit there and just wait for you guys to work it, which is good. You have to have the discipline, though, here to turn it off, to pause the video, and take the time to work it, okay? SO2, I'm just going to say see above because we did that in detail on, what's today? On Monday. Okay. SO3 minus. Go ahead and pause, work the example, and then come back. Okay, so I have no other choice here other than to go ahead and split up one of these pairs. I guess the other choice would be that I give it to one of the other oxygens, but that's going to mess up the formal charge. Okay. So if I check the formal charge on this, I'm doing the sulfur, 1, 2, 3, 4, 5, 6. So this is 0, this is 0, and these guys are -1. That is really the best option. I guarantee you, even if you Google this, you're going to see people drawing it like, sorry, get rid of that there. You're going to see them drawing it like this. And what they did in that instance was they gave, let's see, this electron to this oxygen in order to avoid making that double bond. I don't even see how you could actually come up with that. I'm gonna have to look at that one. I swear I've seen people draw it like that online. I'm sure there's a way. I'm not going to waste your time doing it right now. Okay, this structure we have here, great. So, sorry, I lost track of where I was. Okay, electron geometry, tetrahedral, molecular geometry, 4 groups, one of which is a lone pair, trigonal, pyramidal, slightly less than 109.5. Okay, sorry, I'm going to double check myself here and make sure I did this structure right because now I'm second guessing it. Okay, single bond there, single bond there, single bond there, and the double here. Alternatively, yeah, so the alternate version would be just taking this electron and moving it over here. And so you'd end up with this, which is interesting because you'd actually get the same answers for the electron geometry and the molecular geometry and the angles if you did it this way. So all of these ones you would get the right answer for. It's just that this isn't the correct Lewis structure. But like I said, I guarantee you if you look on the internet, there's going to be tons of people who drew it that way. That's because this one strictly, follows the octet, but that's not the priority. If we look at these formal charges, let me do that in red. It's a good example of revisiting formal charge and drawing Lewis structures. If we look at this, 3, 4, 5, we've now made the sulfur +1 and the other oxygen -1, whereas here they can stay as 0. So this is definitely our best Lewis structure. And I don't care that we broke the octet rule because that's fine with sulfur. It doesn't change these answers though. Okay, next one, go ahead and pause. Okay, this is extremely similar to water. 4 groups, 2 of which are bonding. So the electron geometry is tetrahedral, the molecular geometry is bent. The true bond angles are less than 1 and 9.5. Okay, we need to do one other example for 5 groups. I want to start with this one. I think PCl5. Let's go ahead and look at the real examples. Yes, PCl5. Okay. So let's go back and pause the video for a second. I'm going to use this blank page, and I want you to do the Lewis structure for PCl5. So go ahead and pause the video, work through the Lewis structure for that, and then we're going to go back to the simulation. Okay, this is another one where we have to break up that lone pair. 1, 2, 3, 4, 5. Yep. 1, 2, 3, 4, 5. Sorry, just checking this because something doesn't look right to me. Bonds, we're missing a pair there. Let me check the periodic table and make sure I've got this in the same place that I want it to be.